Okay, Chapter 6 of Pearson, Basic Chemistry, Ionic and Molecular Compounds. We'll talk about ions, transfer electrons, and that's really what happens there. Ionic compounds, name it and write ionic compounds, polyatomic molecular structures, how compounds share electrons, and how some, basically, in their sharing, they choose to send most electrons to one of the other elements, and they're all very happy. You're going to learn those kinds of concepts. And these, the principles from these are why compounds work the way they work, and we use them the way that we use them. Okay, most elements except the noble gases are found in nature, combined with other elements in compounds. We note the noble gases are in group 18. They're noble. They have 8 electrons around. They're very happy sitting there on their throne doing nothing. That's it. They don't really want to interact. They don't want to form new compounds. But most of the other elements on the periodic table, and I passed out the periodic table for you to have there in front of you. Did we get those passed out around? Mm-hmm. I'll take the other extras back. I'll need one too. Thanks. So we have the periodic table, and if we look in nature to find these, oftentimes we have to refine them because they're combined with some other elements. So we dig them out of the ground or pull them out of somewhere, get them out of plants, and we have to do something to them to get the original elements. But then there's others that are original element, but again, it has to be refined because it's combined with something. Compounds with electrons are transferred or shared to give stable electron configuration to both atoms, and that's what they do. They're looking to have 8 electrons around each of them. Okay? I glanced at a few of your problems this morning. Some of you are going to miss them because you have 10 electrons around there. The max you want to put around there is 8 electrons around the compound. So when you look around there, you're going to learn more about that today. Okay? And that's what they seek to do. So they say if we combine in this fashion, we can both be very happy. Now, there are elements on the periodic table that don't that are comfortable not having 8. They're found in group 1, group 2, and group 13 of the ones that we're going to cover in this class. So group 1 is very comfortable if it has 2 electrons. Group 2 is very comfortable if it has 4 electrons. Group 13 is very comfortable if it has 6 electrons. But after that, the others want to have 8 electrons around them. You'll learn more about why that's the case. So what they seek to do is have some stable electronic configuration shared amongst it. Okay? And when it does that, it's voila, it's good to go. Atoms lose, gain, and share electrons to form ionic compounds or covalent compounds to obtain an octet. Octet, that's the rule of 8, but we now know 1, 2, and 13. They're comfortable with 2, 4, and 6. Covalent compounds are formed from atoms of nonmetals shared with their valence electrons. Now, we talk about lose and gain electrons. Make a note of the following. Group 1, Group 2, and Group 13 prefer to lose electrons. Okay. Meaning they are oxidized. Group 1, 2, and 13 prefer to be oxidized. They prefer to lose electrons, which means they become more positive. We'll talk about this more as we go, but I want to introduce the concept. Group 14 depends on what it's combining with. But more times than not, it would prefer to lose 4 electrons. But it depends on, it's situational. Be aware of that, so everyone follow that. Okay? But more times than not, it would prefer to lose 4 electrons. Group 15, 16, and 17 prefer to gain electrons. 15, 16, 17 prefer to gain electrons. Okay. That process is called reduction. Sounds a little funny, but it is. It gains electrons, therefore it is reduced. It loses electrons, therefore it is oxidized. You have to let that float in your head a little bit for it to make sense in your own brain, okay? All right? So be aware of that. The concepts I just gave is the basis of the concepts that you are going to use in this class, at this level of chemistry that we're teaching for this class. Follow? Those concepts are the summary. If you can hang on to those, you'll do well in a lot of things we're going to talk about and show you. Okay? So that's kind of your memorization. Put on your PlayStation or put on your date card, okay, to memorize. All right? All right. When elements don't share the electrons evenly, it's called ionic. When they don't share even, when they're not even, they don't play well. So one takes all the marbles, takes all the balls, okay, and the other kid's sitting there with none of the balls. That's ionic. Covalent, kumbaya, love to share. Okay, follow? So be aware of that. These are the concepts that we're going to do over and over again. So I want to mention those to you so you're aware of them in case I don't give them to you in that detail again. This is what you're going to be hearing over and over again. So here we are, ionic compounds. Example is sodium chloride. You can almost always, an ionic compound of group 1 and group 2 with group 17, always going to be ionic. So if it's in group 1 and group 2 and 17, it's always ionic compound. So that's one way you can get it right every time on the exam. Just look at it, see which group it's in, because that's really what drives it. 1 and 2 with 17 is going to be an ionic compound. Don't second guess it. And actually group 1 and group 2, let's just expand it and say with 16 and 17. For this class, don't second guess it. It's going to be ionic. So group 1 and 2 with something from 16 and 17, it's going to be an ionic compound. That's because of the things we studied in the last chapter about electronegativity. The elements on the right side of the periodic table are highly electronegative. They will suck their life right out of anything that has a few electrons. They pull electrons. They basically rob them. Group 1 and 2 say that's okay. We only have 1 or 2 anyway. We're happy to give them up because if we do, we become noble. We move over to the noble gas, okay, and we look like them, okay? All right? So be aware of that. That's what makes it ionic. So that separation in electronegativity, okay, is what makes it ionic. Covalent, this is kumbaya, love to share electrons. The compounds that will share and share without much confrontation will be 13, 14, 15, 16, 17. However, 13 will make ionic compounds. What do you think 13 combined will make a good ionic compound? Just take a guess off something I've been telling you all morning. 17. Get it? So 13 with 17 will make an ionic. Not quite like sodium, not quite like lithium, but it will make an ionic compound. Follow? So 13, what you're learning is kind of right on that edge, right? Right in that part where things start to shift a little bit. Okay? But if it's 14, 15, 16, 17, do not second guess it. It is covalent in this class. Don't second guess it. Where you have to do a little bit harder thinking is when you get to 13. But if 13 is with 17, it's going to be ionic. But 14, 15, 16, 17 combined is going to be covalent. These are things you want to memorize. These are questions I'm going to be asking you on quizzes and on exams. Okay? And you can do it by looking at the periodic table. I will always give you a periodic table. Right? So this shows how we combine it. You've done Lewis structures, and you're doing Lewis structures. What happens here, you have this, you know what group this came from, right? Anybody know which group this came from? Where? 1, yeah. You see how you know it? You just start to look at it. You're getting it. This came from group what? Yeah, 17. So it's going to be covalent ionic. Ionic, right? That's the way it is. You have to second guess it. So it's going to combine. When it combines here, this combines, instead of this hanging onto the electron, it's very happy to oxidize and transfer it here and make this into table salt. It's very happy to do that. This is no argument amongst them. Okay? This is peace and harmony. Okay? Here, these both are from what? Group 17. They combine and form this. And we know that in group 17 forms diatomics. Okay? And that's how they do it. So this is covalent. This is ionic. Does everyone follow? Okay. Ionic simply means there's no equal sharing. Covalent means equal sharing of electrons. It is that straightforward. Here we've already told you this. Ions which have electric charges, atoms lose electrons from stable configuration. We just told you what they are, 1, 2, 3. We've already gone through this, right? This is what we're telling you. When you see these, they're going to make ionics. And again, the 1A, I use the 1s, 2s, and 13s more than the 1A, 2A. If I were teaching an analytical course, I would talk more about the A's and B's, okay? Because there's some other science and chemistry that's related to that. It's more historical, but it's still there in the literature. So when I talk about them, I'm going to be numbering them as 1 through 18. Be aware of that, okay, for this class. Here we show you sodium. It's 3s1, and you know it's 3s1, right? Because it's third, 1, 2, 3. You look at on your periodic table that you have on your handout. You see it's going to have a what? 3s1 configuration. Does everyone see that, right? It's in the third block. It says 1 electron can't hang on to it. I'd rather give it up. Okay, so it gives up the 1 electron, and it's very happy now because now when it loses an electron, you back up 1 block. So look on your periodic table, right? Look at sodium, right? You lose an electron, that's like losing a block. And so where do you end up if you lose one? You go back to what? Neon. Does everyone follow? So elements on the periodic table like to be isoelectronic. Write that word down. They like to be isoelectronic. Iso and electronic. They like to be isoelectronic with group 18, with the noble gases. So if sodium loses an electron, it looks like it's mimicking a noble. Okay? Instead of having on silk, it has on polyester. Okay? If you look at it from a distance, you can't tell it. You follow? Okay? So it's, yeah.
But it's still sodium.
It's still sodium.
It has of the protons in the nucleus, correct?
That's exactly right. You hear what she just said? That's my best statement to say. Very good. She said it's still sodium because it has what? The protons is what gives it its character. Right. It has the same. The protons don't change. Remember, that's how we know an element is an element. And we know that the electron, remember earlier I said I'm only going to give you neutrals. Now you're learning what happens if you don't have neutrals. When you don't have neutrals, they become isoelectronic with something else. That's right, becomes positive. That's exactly right. Okay? So its electronic configuration now looks like neon. You get it? But its protons tell you that it's sodium. Does everyone follow? That's what's happening. So these electrons will move around the periodic table trying to mimic the noble gases. Okay, with their isoelectronic configuration, because it's a very, very stable way to be. It's comfortable living. You get it? It's very, very comfortable to do that. Okay? But that's what's happening. Notice it did it here. This is sodium. This is sodium plus, which is the same thing as neon. Okay? All right? Here, magnesium is in 2, right? So it's only 2 electrons. Say, what the heck? I can drop these 2 electrons, right? And I can look noble. And it also looks like neon, but the protons tell you that it's not. It tells you it's what? We're magnesium. Does everyone see that? And you can count all of this from the periodic table. Now, some of you may choose to memorize it, but you're going to have a periodic table, so I get used to just look at the periodic table and get my answers. So what are we learning? The ionization energy of the nonmetal atoms, 15, 16, 17, is high. You know here, these are the ones that I told you about earlier. Okay? Rather than lose electrons, they really gain them. And it kind of makes sense to you, right? You're trying to get the nobles east, you just go that way and pick up the electrons.
Well, it's easier to pick up 2 than lose 5 for whatever, 6.
Yeah, you get it. That's exactly right. It is, and it sounds too simple when we talk about it this way, but it really is what's happening. The energies know all of this. Okay? All right? And they find a way in nature to accommodate itself. This is all natural for nature to do this. Okay? It's trouble for us as scientists trying to figure out how to reproduce it. But for nature, it's a piece of cake. So here you have it. This is what you already know now, right? You have chlorine, and you notice the electron cloud changes each time. I don't know if you paid that attention or not. Notice here, you had this electron cloud. You lose that electron, the electron cloud goes down. You get it? Because it's minus an electron. What gives us volume and size? Electrons. You lose electron, and you notice it went from this is sodium. Sodium went from 3 to 2. Remember the example in the football stadium? Now you're moving closer down to the field, right? Where the golf ball is in the center. Same thing happened here. But in the case of this, we picked up another ring, didn't we? We picked up we picked up one electron. It said, wow, this is really cool. Okay? I'm noble. But my protons tell you, yeah, when you card them and check the ID, you say, yeah, you kind of look like you should be in the club, but you're not. You get it? Okay, follow? And so that's what happened. The protons are the giveaway. That's what tells you it's still there. And this is what you already know. Here are the things I've already told you. You already get it now. This is the summary of what you know, right? And you just simply look at it and recall. I use just the ones. Does everyone recall that? Okay. You won't hear me use the A's. Okay. This is what we went through. You can now count and to know what the charge is. Now here's the fun part for this class and for this level of chemistry that you're learning. You now know the charges simply by looking at the periodic table without memorizing them all. 1 is going to be what? +1. 2 is going to be +2. 13 is going to be +3 because it takes 3 steps to get back to noble. Get it? Carbon's going to be, and we took carbon typically likes to be positive. This 14 typically likes to be positive, and for most of the things I think that I'm giving you in this class is probably going to be positive. Okay? All right? This level of chemistry. So you count 1, 2, 3, 4 steps back to noble. You look at nitrogen, you got what? 1, 2, 3 steps. So that tells you it's -3. That's how you know them. You don't have to memorize these. Just simply look at the periodic table and count how many steps to noble. Okay? That's what this is showing you. So you can memorize if you like. We also show you how to name them. So let's talk about how we name them. We simply, well, let's see here. Here, the positive ions, all positive ions are simply named as a simple name. Real deep stuff, isn't it? You know it's lithium. If it's a positive ion, it's lithium. No changes whatsoever. That's it. Does everyone follow? Positive ion, lithium. What's the positive ion of sodium? Duh. Sodium. You know, you get it? Now, of course, on the exam, I'm going to put sodium. I'm going to put sodium, sodiide. I'm going to put all kinds of things like that. Don't let that trick you. It's just sodium if it's a positive ion. The negative ions, on the other hand, like to go for a ride. IED. They're the ides. I call them the rides. Get it? There you go. You just simply drop the E, ide. Got it? Nitrogen, gonna be nitride. Drop the N's, right? IDE on it. If you get panicked and you just cannot remember, like bromine, right? And you can't remember, do I drop the NE, the INE? Can't drop it at all. Go for it and at least put bromine ide on the end of it. At least you'll tell me you knew it should have been ide, you just can't spell. You get it? You know it should be ide. So don't leave the ide off of it, of all things. You follow? Okay? So remember that. Now all you guys are going to put it and pretend you can't spell. You're right. Okay, you got it though? This is it. This is how we name them. You now know how to do the charges by using the periodic table. You know the positives, simply name them, and go for a ride. IDE. Here we show you some examples where they're used. One of the things I want to make sure you're aware of, hypo tends to mean down. Hypo means less or down. You got it? Per means up, elevated, so be aware of that. So you'll watch for those terms because I may ask this type of thing. I may ask you, was this elevated or depressed, right? Hypo is down, it's less, fewer, lower, all those terms. Hyper, above, more. So for example, here we show you some of the consequences of sodium, and we know where we get sodium from: salt, cheese, pickles. So for those who have this sodium craving, eat some cheese or pickles, right? It's just, it's kind of, like on your salads, right? You got to put the salt on your salad. You have this beautiful vegetables, right? But okay, we've got to have a little sodium taste. All right, ask for some cheese and put it on there. Okay, all right. You get it? Or put a pickle on it. Sorry, I'm sorry.
I said I'm hungry.
Oh, okay. Maybe we should have classic one at a restaurant one day. That might be a cool thing to do. We might do that. I'm insane enough to do it. Okay. All right, potassium. Bananas, okay? This is kind of one I try to make sure I do. I'm not a huge banana fan, okay? And bananas for me have to be just right. But I try to have one in my bag now. I try to make sure for this very reason, just a basic health reason. Okay, milk. I am not the milk person, but I always eat cheese each day. So just showing to get my calcium, these types of things. And the younger you get, yeah, right. The more you have to do these kinds of things. It's just the way life is. Magnesium. Here, nuts, whole grain. I'm pretty big here. My biggest issue is I go through these things when I stop going to the gym, and then my son's my workout. He's my trainer, right? And like for me, I want to like lose mass, right? Well, this kid, he's
Bulk up?
yeah. So he puts me in the gym, right? I'm trying. He thinks I'm trying to. I say, man, I thought that's what he said. No, I thought you were trying to bulk up. Oh, I'm not going with you anymore. Okay, put me on the treadmill. Just let me kill myself. But yeah, that's what he does. He walks around like this, popping buttons kind of thing. He thought that's what I wanted to do. I said, man, look what you did to me. Anyway, so now I got to figure this thing out again. My point here is, though, these things are healthy for you with exercise. Okay, nothing works without it. Just real life. And chlorine here. Chlorine gets a bad rap, but we kind of need it. Okay, so be aware of these. I may choose to ask you some of these, so be aware of them. I'll try to warn you before the exams which ones. And that is typically my habit. Exam prep, I'll tell you. You ask me, I'll tell you. Okay. Ionic compounds, you now know this, right? Positive, negative side, right? What happens? One gives up the electron, the other takes them all to their side of the bed. Okay, they pull all the covers, you get it? They have it all. That's an ionic compound. And we know good ionics are 1 and 2 with 16 and 17. Here, sodium reacts. So what happens? Sodium here reacts with chlorine, and they react at their valence electrons. You know what valence electrons are now, right? And you know how many. You know how to count them simply by looking at the periodic table. Okay? And when they react, sodium, instead of collecting electrons, it gives up the electron. And chloride said, great, I'll collect them. We both mimic being noble. Chlorine mimics argon, and sodium mimics neon. When I say mimic, that means isoelectronic with the protons, as you well pointed out, gives it away. This is what it looks like. This electron populates here, and here's what happens. And notice the size has changed. Does everyone see what happens? Very important. It loses electron, the cloud decreases. But gains electron, cloud increases. This is reduction. This is oxidation. Okay? You have to have both oxidation and reduction. In this course, based on the requirements for Davenport, we do not go into any further depth of oxidation and reduction. This is your lesson of oxidation and reduction. Okay? If you have oxidation, you must have reduction. Right? And that is what happens when these elements, something's going to be oxidized and something's going to be reduced. Okay? So, sodium is oxidized, but it causes chloride to be reduced. Therefore, sodium is the reducing agent. It's the agent of change for chlorine. Chlorine is the agent of change for sodium. Chlorine itself is reduced, but it is the oxidizing agent for chlorine. Does everyone follow? Okay, there's your electron oxidation reduction. It's going to repeat. Here, you notice what happened with magnesium. Now, this is where I think this author does a good job with showing you the pictures. I think he does a marvelous job of this. It's one of the best I've seen. Here, magnesium. We call these two electrons, right? You draw the little structures. Okay? You draw the little structures here. What happens? Those electrons transfer in there, form a bond, but it's an ionic bond. It's not a covalent bond. Okay? So this loses electrons, goes down, gains electrons, goes up. That's what it looks like. So what we'll have is 2 electrons and 1 electron. And when this is the case, what's happening is we're going to show you how to write these by crisscrossing these elements. But notice here, it has to be electronically neutral. Since magnesium has a +2 and chloride has a -1, we need to have 2 of these. Get it? This is why we need 2. So there's several reasons why we need 2. One is 2 here. Remember I told you, you kind of get that, without any more information, how many times would magnesium like to comfortably bond? This is where we get the concept from. So there's 2 here, and that's where we get the +2. Chlorine, without any other information, how many times would it like to comfortably bond? Once. So you put 2 of them together, you got it here. But it has to be neutral. So this is the math that these electrons undergo. They do this all by themselves without our help. But we have to know how to do it to see it's neutral. Okay? So when we write these, the subscripts at the bottom represent the electrons transferred or either the electrons transferred or collected from the other element. Case of magnesium, it transfers 2 electrons, so you'll have a 2 at the bottom, so you get mag2. Case of chlorine, it's 1 electron works, so it's a 1 here, but we don't write 1s, and you get MgCl2. So everyone kind of follow that. So we write these that way. So here's what you want to know, is we basically crisscross these charges. But now you see why. Because you have sodium here and it has 1 dot, right? Sulfur has 2 dots floating around. So you need 2 sodiums to go with that. Okay? And so it comes out and it's electronically neutral. So it's -2, crisscross, and we get the answer. We're going to practice that. Show you some other examples here. Sodium, this is it. Well, same example. Notice electron density went down here. In this case, electron density increased. Okay? So naming ionic compounds, we already told you how to name them, did we not? Right? What's the first part of it? The first part, we always write in chemistry, compounds are written with what's called the electropositive part first and the electronegative part second. That is the convention for writing compounds. We always do that. We write the electropositive part first for all compounds in chemistry. And we write the electronegative part second in chemistry. And we always drop the ending in ionics and write at what? Go for a ride, right? IDE. So to name them, you name the first part, name the second part, IDE. It's that straightforward. Don't try to count how many. You just say, well, I thought I should count them. You do no counting. Make a big note, a big poster board, paint it on the side of your house, your car. Do something, okay, to remember this. You don't, when it's an ionic compound, you don't count the atoms. You simply name it with IDE. Do not count. So don't say, well, I thought I should count. Don't think about that when you do not count. Okay? And how do you know it's ionic? You know it's group 1 and group 2 with 16 and 17. Therefore, it's ionic. So I'm just going to name it lithium fluoride and be done with it. I'm not going to worry about how many there were at all. Does everyone follow that? Okay? You do not count. Okay? So be aware of that. So make yourself, write it in your hand, do something. Get a tattoo. Do not count. Okay? And here it is. These little rules, you can memorize them, but I just told them to you. Okay? Simply name the first part, last part, followed by IDE. Okay, so this is magnesium nitride. See it there? No numbers in it at all. Okay? So you do not count. In the D region, and F region of the periodic table. We'll talk more from the D region. You know where the D region is, the periodic table now, right? That's the little valley here. The elements in the D block of the periodic table have variable charges. The variable charges for the level of chemistry you're going to be for the level of chemistry that you're involved with, that variable charge is always going to be positive. We're not going to do any Berkeley chemistry here. Okay? Or MIT. We're not going to even do U of M. Okay? So the D block is going to be variable. So they're all going to be positive. So here's something to note, and we'll come back and tell you more about the variable charge. Group 1 through 13 for this class will carry a positive charge. Okay? 1 through 13 will be positive. Actually, 1 through 14 will be positive. 1 through 13 is always positive. For this class, 1 through 14 will be positive. 1 and 2 we know are fixed charges, right? They're set. What's group 1? Plus 1. What's group 2? Yeah. What's 13? What is it? Plus 3. Yeah, you just count back. Just look at it and count them. Right? You got 1, 2, 3. Okay, 3. Boom. Okay, you get it? So we know that. But these in between here are going to be variable. I'll give you some indication of what they are when I ask for them. Okay? You'll know. I'll tell you what it is, or I'll give you some really big, clear hint of what it is. Okay? So variable charges here. But this is 1, this is 2, this is 3, and 14 is 4. So the negative charges are going to be 15, 16, 17. And what we call polyatomics, which you're going to learn. Okay? What's going to be a charge on 18? Nothing. All right, neutral. No charge. Noble gases. They sit around, they do nothing. Okay? Here we show you some examples here. Okay, but we'll help you through these. We'll give you really big hints as to what these are, the variable charges. Okay? That level of chemistry of learning how to know them won't be taught in this class. So here they are. This is what you'll want to know. 1 plus 2 plus 3. Here you notice it kind of opt out. Doesn't like to talk about these because of the chemistry involved here. Okay, this is variable chemistry here. But for this class, we're going to limit our scope to these being positive. These are going to be negative, and these are neutral gases. So we'll tell you the others. So do not memorize this. But I do expect you to know your metals now, right? Nonmetals and your metalloids. When we name a compound with a variable charge, we give we tell what that charge was, essentially. We name it like a salt, but telling how many. Does everyone follow? Okay? So the last part we know is going to go for a ride, right? IDE. The first part is going to say the name, just like it always does. But between there, you're going to put a big Roman numeral telling what the charge is. That is the convention. Okay? Someone once asked me, why in the world do they do it this way? Well, I don't know. I wasn't there. A bunch of old fellas years ago in Russia or Germany, and then they started to argue across the Europe continent about what it should be, and they couldn't agree, and they said, doggone it, this is what it's going to be. Then a bunch of old guys got together and formed a union called IUPAC, and they said, we're going to make it law, and we don't care what Anthony thinks about it. That's it. So there's a why. It's a mama said so. Okay? That's why. It does have some rhyme and reason to it, but it's simply by convention. It's by rule. Okay? So that's the rule. So if I tell you that the charge on here is +3, you just tell it, +3. So this is iron 3 chloride. You know it's iron chloride, right? But since it's in the variable group, in the D block, we have to tell it what charge it is. So the smart way to write these is simply write it as an ionic first, then go back and determine the charge. You get it? Then leave your little space, determine the charge, and write it in. Don't try to figure it out on the way. Just write, you know it's ionic because it's here, right? So you write it as an ionic. You write the first name, the last name, that's it. Then find some way to know the charge and put it in between it. Does everyone follow? That's how we name them. That is by rule, that is by convention. There's a special group of compounds we call polyatomic. You simply have to memorize them. This is your group to memorize. This is it. This is your take home. You will have to know these. These you treat, okay? These are the names. Ammonium happens to be a positive polyatomic. Most of the others are negative. You see that, right? So ammonium will be written first because convention is we write the positive part first. Okay, that is by rule. And then we name them nitrate. So if we had sodium and nitrate together, it would be sodium nitrate. If it's a salt, you do not tell how many. Got it? If it's iron with nitrate, iron is a variable. So we have to say it's iron 3 nitrate or iron whatever nitrate. You follow? Because it's in the D block. So if you look and you see it's in the D block, remember you have to put the Roman numeral in. The D block carries the Roman numeral. Okay? Everything else does not carry. It doesn't carry at all. It doesn't carry anything. So you have to memorize these polyatomics. Certainly these you'll want to know. Well, you'll have to just memorize them all. So here's some examples of where they use ammonium nitrate. You know, a lot of agriculture use ammonium and nitrogen compounds, sulfur compounds too. So we use here the calcium sulfate to make these casts because it kind of makes a nice compound thickener there that doesn't degrade in water. So we name them the same way. We memorize this part. These you memorize. You go from trait to trite, fate to fight. This is memorization. You have to memorize the polyatomics. So you want to get going on those. Okay? Here we are. Full list of polyatomics. I expect you to know this one. Carbonate on the C. I expect you to know carbonate. I expect you to know acetate. On the nitrogens, we're going to limit you to one in bowl, nitrate. In chlorine, I'm going to limit you to the one, chlorate, phosphate. So everything in bold is what we're going to limit you to, except in this case I expect you to have carbonate and acetate. So this is your table. Does everyone follow? These are the ones I'll expect you to know. So you now know how to name them, don't you? Sodium sulfate. Why did we put a 3 here? It's in a D block. Follow? Put a 3 here because it's in a D block. Here, this is not aluminum is not in a D block. You simply name it aluminum carbonate. Okay? And here we show you some examples and what they're used for. We expect you to just kind of be familiar. And this is everything we just told you about how to name them. Okay, let's continue chapter 6 by talking about nomenclature of molecular compounds. We've already gone through a work session to talk about this, and actually you now know how to do it. So what we're going to do now is walk through the lecture principles to make sure you have them and you know why you've been doing what you've already learned to do. Molecular compound contain 2 or more nonmetals that form a covalent bond. How do you know the nonmetals? You looked on the periodic table, right? And nonmetals are 15, 16, 14, 15, 16, 17, and 18. So you know they're nonmetals. So when you put 2 nonmetals together, they're going to be covalent. Covalent means they're going to share the electrons evenly, which means they're going to look to fulfill the octet rule. So if you look around any single atom, it's going to have 8 electrons around it. Okay? Valence electrons are shared by the nonmetal, covalent. You know how to do valence electrons by looking at the periodic table and doing the electronic configuration. You want your SPDF. When 2 or more atoms share electrons, they form a molecule. Not an ionic compound, but a molecule. Okay? All right? Here, an example, hydrogen is diatomic. It exists in natural state as a diatomic molecule. 2 hydrogen atoms share electrons to form a covalent single bond. That's what it does. It shares 2 electrons. And it's very happy in that electronic configuration. Helium becomes, each hydrogen becomes stable like the nearest noble gas. You get it now, don't you? All right? It's isoelectronic configuration. Okay, it's isoelectronic with helium. You get it? That's what's happening to these. We've already talked about this, and we've already done this in the work session. Here it is again. You've seen this before. This is an ionic compound, isn't it? It's ionic because it transfers these electrons into this space, growing this electron cloud and reducing this electron cloud. But in the case of this molecular compounds, this molecular compound, this element has 7 valence electrons. It comes together with the other one, 7, and it forms a covalent bond, equal sharing. There's 8 electrons. Notice here, this is a good diagram. Notice here, if you see the circle here, this has 8 electrons. See the circle here? It has 8 electrons, and it shares 2 common electrons equally. Okay? This is a nonpolar compound. There are no different elements. When we name them, you now know how to name them. And let me make you aware now that there are some flaws in naming these covalents. You will not have any compounds on your exams that have exceptions to the rule. Okay, yours will be pretty straightforward. Okay, so be aware of that. And remember, you have to memorize, we've already told you, you have to memorize the Greek, mono, etc., di, etc., tri, tetra, and so on. In a molecular compound, prefixes are used to indicate the number of nonmetals. So the way we draw, a good way to draw this is to simply write it like you would for a ionic, and then tell how many. Okay? So here we have nitrogen dioxide. Typically we don't say the mono on the first element. Okay? But on the second we use mono in many cases. There are some exceptions. If we're in this class, if you do a covalent and you put mono on the end because it's 1, you will not lose credit. Okay? You're not going to be familiar with the exceptions. And we're not going to spend time trying to teach you all the exceptions. We're going to try to get you to learn the basic rule for how to do it, so everyone follow. So I'm going to do my best not to give you any exceptions. If I do and I remember after I've done it, you're going to get your credit for it because you follow the system. Here we have carbon monoxide because it's 1 carbon. Here they are. You can now memorize them. Okay, put this on your watch band. Put it inside your or whatever when you, okay? And Yes, you've heard me say it before. It's a good thing to take on dates. You'll be a hit on your date. Okay? Mono, di, tri, tetra, penta, hepta, hexa, hepta, octa, nona, and deca, and that's as far as we will go. Okay, after that it goes on deca, etc. So you'll need to memorize these. This is how we talk about it. And here are some examples. Here we have sulfur dioxide, dry ice. So we use at the Beyonce concert, okay, or the Keith Urban concert, or the Tim McGraw or George Strait concert if you want dry ice. Yeah, manufacturer rayon here, carbon disulfide. Here we have, look, dinitrogen oxide, okay. Here we have nitrogen oxide. Notice it didn't use the mono here, okay. Okay, so be aware of these. The molecular compounds are perhaps the most inconsistent area of nomenclature we have, just the way it is. There are reasons for that. We won't get into it. You have to just memorize a lot more rules. But again, if you had said mono here, I would have been okay, because that tells me you know and you understand the system. Does everyone follow? So be aware of that. Sulfur hexafluoride and sulfur trioxide, and what they're used for. So we've already gone through this in the work session, so you're going to be good there. So let's just name this what we would name it. You know that now, right? Nitrogen trichloride. Okay? Does everyone get that? We're okay there? Okay? For diboron trioxide, what would it look like? Yeah, O3. Yeah, you got it. Okay? Don't break the system. It's just a systematic way of doing it. Once you get the system down, you go with it. So you got it there? Okay? Then we write there. And here's the entire table, okay, for how we name absolutely all of these. Guess what, folks? You're going to get a long break.
186.